is going to speak about another proof of Jayne-Rogers theorem.
Indeed. Although I'm only going to speak about that at the end. So I guess I should first thank the organizers for having me here. Are any of them here? So I'm going to talk about joint work with Raphael Kawa. And I'm going to keep things very elementary, but I am going to give some sketches of proofs. I won't give the full details, but you can find the full details on my website. So it's sort of like an advertisement for a recent paper. So I guess I want to start at the very beginning. The simplest dichotomy theorem in descriptive set theory, this is the perfect set theorem. So in the case of analytic sets, this is Suesland's perfect set theorem. It says that every analytic Hausdorff space is either countable or has a perfect subset. This is really the easiest such theorem to prove, but that doesn't mean that there aren't other descriptive set theoretic dichotomy theorems that are just as easy to prove. In fact, there's a natural generalization, the open graph dichotomy, which really is a generalization, but any proof of the perfect set theorem gives you a proof of the open graph dichotomy. So it's just as easy. The open graph dichotomy says, let's see, if you have an analytic Hausdorff space and an open graph, then either it has countable chromatic number or it has a perfect clique. Okay. Now there are a number of ways of trying to generalize this to higher dimensions. Some are hard and some are easy. I want to start off by talking about one that's very easy. I will need two definitions. So let's see. So this is ugly language. An n-dimensional dihypergraph on a set X is just a set G contained in X to the n, consisting only of non-constant sequences. So they don't have to be injective, but they shouldn't be constant. So I'm going to want to talk about a generalization of the open graph dichotomy to Aleph null many dimensions. So this is the relevant notion of graph. Whoa, that doesn't go up. Right. I need to be able to talk about an analog of a perfect clique. And I have a truly terrible name for this. The evenly splitting n-dimensional dihypergraph. This is the dihypergraph. I guess I should give it a name so I don't have to keep writing that. So G sub evenly splitting, guess, is the dihypergraph G sub ES on the on bare space, just consisting of all omega length sequences of elements of bare space. They share some common initial segment T, and the nth element of the sequence has entry n at the next point. And what happens after that can be whatever you want. So consisting of all sequences of the form T followed by I followed by B of I, where, so this is for I in the natural, so that's an omega length sequence of elements of Baire space, so this is where T is a finite sequence, and B is a sequence of elements of Baire space. So you just go into the tree and then you just go across, however you want. Okay. Now, I mean, I don't want to write down the definitions of independent sets or colorings for these things. It's just like in the two-dimensional case, right? A set's independent if there are no hyperedges in the set. A coloring is a function where the preimage of each singleton is independent. Okay. So the natural generalization of the open graph dichotomy is the following. So suppose X is an analytic Hausdorff space. And G is a box open n-dimensional di-hyper graph on X, then exactly one of the following holds. One is that the usual chromatic number of G is less than or equal to aleph null. That just means that you can cover the underlying space with countably many sets on which the graph is trivial. Or two, there's a continuous homomorphism so this is a map phi from Baire space to X. It's a homomorphism from GES to G. And the proof of this is identical to the proof of the open graph axiom. So this is nothing deep. This is just as easy to prove as the perfect set theorem. So this is an example of the easiest sort of dichotomy theorem to prove in descriptive set theory. So you have the tree. I'll draw it here. So you have the complete omega-ary tree, omega to less than omega, given any t, right? And any sequence b of 0, b of 1, b of 2, b of 3, you look at 0 followed by b of 0, 1 followed by b of 1, etc. This sequence, so t0, b of 0, t1, b of 1, that omega length sequence is a hyperedge.
Again, you talk about n-dimensional.
Yeah, so this is a big N, so it's an omega length sequence.
Oh, okay.
And can you say again what's a clique? What's a clique?
In a regular graph, a clique in a regular graph is just a set of points, any two of which are related. But that's not what we're talking about here, right? This is the generalization of a clique, that there's a homomorphism from this to here. I mean, you could try using types and things, right? This is just sort of the type that no one cares about when they try to do real generalizations to higher dimensions. This is the type that gets ignored, okay? But somehow here it's going to be a central notion. Okay. Is it okay, or? Okay.
I still haven't understood why there's only one GES. Doesn't it depend on B? I mean...
No, it's the set of guys of this form as T ranges over here and B ranges over here. It's the set of all such sequences. So given any T and given any B, you get an omega length sequence. And I'm saying it's the guy consisting of all of them. Maybe I should write it down.
You get a lot of sequences.
What's that?
According to which eye you took.
No, I is the guy indexing the sequence. I is indexing the sequence. I is the index.
So it's a sequence of sequences.
Okay, yeah, right, coming along.
Here, I'm going to write it down.
Okay. Your continuous homomorphism, is that supposed to be one-to-one?
Right now it's just a continuous homomorphism, but I'm about to make a comment about that.
Then it could be constant.
Our definition of dihypergraph is that it doesn't contain constant sequences.
No. But in part 2 over there, phi could be a constant function.
No, it couldn't, because dihypergraphs can't have constant sequences.
No, I'm not saying that it's to a constant
phi
sequence.
would be a constant.
If phi is a constant function, there is an edge here. It would be mapping to a constant sequence. G can't have constant sequences. Am I missing something?
Yeah.
Oh, okay, yeah, because there's typing going on, so it's, oh yeah, sequence is to sequence, okay, yeah. The GES is a different type from N to the N. Okay, now I get it.
So what is the topology on N to the N? You talk about the continuous homomorphism.
It's bare space.
That's the bare space.
Yes.
But the G as a subset of the
G-
S to the N is
Up-
open.
G is a subset of X to the omega,
As
and it's box open there.
okay.
So it's really
the
phi
box
to the,
topology.
What's that?
Opening the box product.
Yes. Yeah. When I say box open, I mean open in the box topology. So it's not finite support; it's full support.
phi to the N is what's going from GES to G.
Yeah. People use different meanings of from, and I've used both. There is a remark concerning your question about injectivity. So if G consists only of injective sequences, then every homomorphism from GES to G is injective. That's a simple exercise. So much of the time, these things will be injective. Okay, so what have I done so far? I've mentioned a trivial generalization of a trivial generalization in a terrible language. This should piss you off. Why? Okay, so in descriptive set theory, there's a number of rather difficult dichotomy theorems that can be proven by first applying an auxiliary graph theoretic dichotomy and then doing some sort of topological construction. It turns out that this is an example of a graph theoretic dichotomy theorem for which a number of well-known and a few new dichotomies are direct corollaries. You don't have to do any construction afterwards. So there are a number of old theorems of descriptive set theory which are really just special cases of this. This is sort of the combinatorial core of those theorems. So now I should tell you what those theorems are. The first and one of the most important for this talk is Hurevich's characterization of F sigma sets. So, I suppose I should say to whom it's due. I suppose I already have, at least in part. So Hurevich started it out, and then I guess Kekris, Louveau, and Wooden later improved it. So what's the theorem? So suppose X is a metric space. And A contained in X is an analytic set. Then exactly one of the following holds. Either A is F sigma, or there is a continuous reduction, by which I mean a wage reduction. So this is going to be a map pi from n to the less than or equal to n, and in a moment I'll tell you what topology I have in mind, to x. It's going to be a reduction of bare space to A. Right, so by a reduction, I just mean that a point is in here if and only if its image is in here. Okay. What is the topology here? Well, the normal topology on bare space just consists of these big N sub S's, right? The guys extending S. I want to look at the smallest topology here, making the analogous things clopin. So let big NS star just be the set of T's. So now these sequences can be finite or infinite length, just such that Sx is extended by T. And I want to look at the smallest topology, making all of those sets clopin. That's the same as the topology generated by sets of the form NS minus the union for n in some finite set of NS followed by n. Oh, I forgot my stars. Right, and it's easy to see that bare space is a dense G delta there. So it's going to be a complete sigma 0, 2 set, a complete F sigma. So why is this? Oh, I guess I wanted to make one side note, right? That Andrew and I were talking about. This is my current favorite go-to example when someone complains to me that I always work in this weird generality and I don't really get anything out of it. When Kekris, Louveau, and Wooden, what did they do? I mean, Hurevich is really the one who proved this. Kekris, Louveau, and Wooden, see, I still need the picture board again. Kekris, Louveau, and Wooden proved the separation version. They proved that if you've got an analytic set A and an arbitrary set W, then either there's an F sigma set separating A from W, or you've got one of these maps which is sending bare space to A and the finite sequences to W. If I had in the statement of the theorem said X is a polar space, that would have looked like a real generalization. But when you're working in this generality of a metric space, they're trivially equivalent because you can just apply this theorem to A sitting within A union W. So this is a nice example of how working in the mathematically natural generality is superior to working in the sociologically imposed one. in any case. So let me just sketch how to prove this, because it really is just a corollary of this fact. Okay, I'm not going to check that they're mutually exclusive. That's an exercise. Let G be the dihypergraph on A consisting of all sequences. So I guess I should name them xn converging. So all sequences in A to the n, right? Converging to a point of x minus A. So if you've got a subset y of A on which this graph is trivial, that's an independent set, then the fact that there are no such sequences in there tells you that its closure is contained in A. So if your chromatic number is countable, then you're the union of countably many closed sets. Moreover, this dihypergraph is trivially box open, because if you've got a sequence that lives in there, you can put a ball of radius 1 over n around the nth element, right? And then convergence doesn't change. So, by our dichotomy, we can assume there's a continuous homomorphism. I'll call it pi. Okay. And now we want to map not on bare space, but on omega to the less than or equal to omega. How do we get it? The fact that this is a homomorphism, this is another exercise which I won't check, but it's trivial, tells you that for each finite sequence T, the sets of the form pi of n sub t followed by n converge to a unique point xt. So this is a two-line proof. And when I say converge, I mean it in the strong sense. I mean that given any open neighborhood around xt, all but finitely many of these are contained. Okay. So now just extend pi to n to the less than or equal to n. Just sent pi of t to xt, and that's your continuous reduction. So that's Jurevich's dichotomy. There's a little side remark. Often when people prove maybe I won't even write this down, but often when people prove this, they additionally note that you can take this map to be injective. Okay? But typically that sort of result follows when you have a nice canonical object like bare space sitting within inside of here. And it's, so what do I want to say? Suppose you hand me a continuous reduction from here to here of bare space to A, then I can hand you a reduction of bare space to itself such that the composition will then be injective. So the injective part just follows for free. Okay, so that's the F sigma dichotomy. There's also the K sigma dichotomy, which I'll mention briefly. So that's due to Jurevich Kekris, and Saint-Raymond. So again, suppose X is a metric space. And A is analytic. Then again, exactly one of the following holds. Either A is contained in a K sigma set, so that's a countable union of compact sets, or there is a closed continuous injection. Pi from bare space to A. Let you stare at that while I erase it up. So this turns out to be both a special case of the F sigma dichotomy and a special case of the hypergraph dichotomy. I'll just say a line or two about each without going into any detail. So, proof one. Fix a compact, fix a metric compactification. I almost said a compact metrization. A hat of the closure of A with an X and now apply the F sigma dichotomy to A, sitting within the union of A and the compactification minus A bar. And it just falls out. So that's one proof. Here's another proof. So when I say proof in this context, I mean something very short. I don't really mean a proof. What's the other proof? Let G be the n-dimensional di-hypergraph on A consisting of all sequences xn in A to the n. I guess I want them to be injective now. Injective sequences xn to the an with no convergent subsequence. It's easy to see that independent implies pre-compact. So having countable chromatic number implies you're contained in a K sigma. Otherwise, you just apply the dichotomy. You get a continuous injection because these are injective sequences. You just have to check that it's closed. And that's, again, a short exercise. So, okay. So far I've mentioned two classical facts about the complexity of sets at a very low level. So these are very elementary things. I now want to shift my attention to a topic that's become a bit more popular in recent years, and that involves the complexity of functions rather than the complexity of sets. Okay. And the very first thing I want to do is state yet another triviality. I want to point out the fact that one can at least get some sort of simple information about the complexity of functions from these sorts of dichotomies, in particular from the F sigma dichotomy. So suppose X is an analytic metric space. I guess for what I'm about to state, Y can just be any topological space. And phi from X to Y is Borel. Well, what does it mean, for example, for phi to be F sigma measurable? So F sigma measurable means that preimages of open sets are F sigma. That's usually called being bare class 1. So exactly one holds. Either phi is bare class 1, or there is a continuous function phi, I have a phi, C from bare space, no, from the extended bare space to X such that the composition reduces bare space to an open set. So the point is that this is a complete sigma 02 set sitting within here, so continuous functions obviously can't do this. Being bare class 1 is as soon as you go beyond bare class 1, that's exactly where you can precompose to get a reduction of a complete sigma 02 set. And this is truly trivial from the F sigma dichotomy, right? If you're not bare class 1, that means there's some open set whose preimage is not F sigma. Apply the F sigma dichotomy to that set. That's your psi. So there's nothing to this. I mean, the point I want to make is simply that you really can get direct information about complexity of functions from complexities of sets, from information about complexity of sets. Now, there's another equally trivial fact where if you replace F sigma measurable by G delta measurable, so preimages of open sets are G delta, well, the same proof works, except you get a reduction to a closed set. Okay. So now I have to once again justify why I'm mentioning so many trivialities. So one of the things that has come up recently for people who are interested in complexity of functions is understanding these sigma decompositions. So let me give you an example of a trivial theorem for bare class 1 functions. This is a simple exercise. Being bare class 1 means exactly that whenever you hand me an epsilon greater than 0, I can cover X with countably many closed sets such that on each of the closed sets, whenever you have a sequence of points converging to some other point, and you look at the images under phi, so this is the image of this guy, and you look at the epsilon ball around him, these guys eventually land in that epsilon ball. So that's just a simple rephrasing of being bare class 1, that for every epsilon greater than 0, you can cover with countably many closed sets, such that you satisfy this weak sort of continuity property, right, relative to epsilon. What doesn't seem to be completely trivial is the Jayne-Rogers theorem, which is the analogous fact for G delta measurability. The Jayne-Rogers theorem is just flip the quantifiers. Being G delta measurable means that whenever you cover with countably it means that there is a covering with countably many closed sets on which the function's continuous. That's a characterization of G delta measurability. That's the Jayne-Rogers theorem. So in particular, if you look at the G delta version of this, so again, you put G delta measurable up there, and you put closed here, right? Well, you get a theorem, and then by the Jayne-Rogers theorem, if you were to put sigma continuous with closed witnesses instead of G delta measurable, so sigma continuous with closed witnesses means there's countably many closed sets on which that cover on which the function's continuous, then you get a perfectly valid dichotomy theorem just by the Jayne-Rogers theorem. Perhaps an important point is that that dichotomy theorem trivially implies the Jayne-Rogers theorem. So if you want a proof of the Jayne-Rogers theorem, you could just try to prove that dichotomy theorem. And I'll spend the rest of my time sketching how that goes. So the proof actually comes in two parts. So unfortunately, I'm not able to realize this is a direct consequence of one of the set dichotomies. It's more like what you do with G0. You first prove an intermediate dichotomy, and from that you do a simple construction. And I'll mainly talk about that intermediate dichotomy. So what is that intermediate dichotomy? Oh, I still had room. Wow, what am I doing? So what's the theorem? You know what? I'm just going to erase that. So now we need slightly beefed up assumptions on our spaces. Again, X is an analytic metric space. But now we'll need something on Y. So let's say Y is a separable metric space. And phi from X to Y is Borel. Then exactly one of the following holds. So either phi is sigma continuous with closed witnesses, so again, you can just cover with countably many closed sets on which you're continuous, or, well, there is a continuous function C, again from here to X, such that Baire space is a maximal set on which the composition is continuous. I might as well switch. Okay. So that doesn't quite seem to buy you Jayne-Rogers on its own, but this is exactly what follows from the previous theorems. I'll very quickly say why, and again I'll give you two ideas of proofs. So for the first one, it's going to look just like the K-sigma dichotomy. Fix a metrizable compactification y hat of y. And now it's easy to check that if the graph of phi is f sigma in x cross y hat, Then phi is sigma continuous with closed witnesses. And then otherwise, the function C from the F sigma dichotomy is all you need. Okay. So that's a simple proof. Another simple proof, proof 2. Let G be the dihypergraph on the graph of phi, which I suppose you want to check as analytic, but it is. Suppose I needed to do that here too. So let G be the dihypergraph on the graph of phi, consisting of all sequences xn, yn for n and n, such that xn converges to some x, but yn doesn't converge to phi of x. And again, you can check that this gives you the theorem. So that's just a sketch again. So what does that leave us with? That leaves us with bridging the gap from this intermediate theorem, which I guess is over here, and the flip of this, where you throw in G delta measurable and you have closed at the bottom. But just like this comment I made before, that injectivity in the proof of the F sigma dichotomy is roughly for free, it's a straightforward construction, that gap is also a straightforward construction. So I'll just state the fact. I have 50 minutes, yeah? Okay, so that gives me 7. Okay. So the fact is the following. So just suppose now that X is any Hausdorff space.
And you have 15 more minutes. It's an hour long.
Oh, it's an hour long. I thought it was 50. Oh, fantastic. I'll say more. Suppose X is a Hausdorff space. Hausdorff space. I can't even see it anymore. Hausdorff. Is it 2F? Now I can't even tell. Okay, so suppose X is a Hausdorff space. What do I want to say? Phi. So bare space and bare space is a maximal set on which some function phi from the extended bare space to X is continuous. Then there is a reduction C. So I'm just precomposing of bare space to itself. Such that the composition has the right property, right? So I want to say that phi composed with C is a reduction of bare space to a closed set, so that's just the same as saying that phi composed with C of bare spaces closure misses the rest. And this is essentially a one-paragraph construction. So that's a sketch of a proof of the Jayne-Rogers theorem. But since I have a bit more time, now I can invent a few more things to say. So this pre-composition trick, the fact that you can do so much by composing with these reductions of bare space to bare space buys you a lot. I should say that what I'm about to talk about I've never written down, so grain of salt. So here's another theorem you can get just by repeatedly applying this trick. There's a 6-element basis under what? Under topological embeddability. For the class of Borel functions which are not bare class 1. And when I say Borel functions, I mean from an analytic Hausdorff space to a second countable metric space. A direct corollary of this and a result of Seletsky is that there's an 8-element basis for those which are not sigma continuous with closed witnesses. I'm kind of a newcomer to this complexity of functions game, and when I first saw what people were doing, I thought maybe this would be the natural way to prove things like the Jayne-Rogers theorem. I can now say that I was terribly wrong, but the theorem still seems interesting. I can tell you what the 6-element basis is. That's simple to describe.
Say basis, you mean for the graphs?
What I mean is that if you've got a Borel function which is not bare class 1, then, if you have a Borel function, then exactly one holds. Either it's bare class 1, or one of these 6 functions from this list topologically embeds into the function. Oh, I have to say what topologically embed means.
Yeah.
Now I understand.
How do you embed function in a function?
I'm a little
I
slow.
thought it was just the graphs. That would make sense.
So here's x, here's y. I didn't do that well at all, did I? Here's y, right? And you've got, what am I drawing? And here's your function f. And now you've got x prime, y prime, and a function f prime. So what you want is a topological embedding of the domains and a topological embedding of the image. C, which makes the diagram. Come here. So how are you going to get this? Well, the first step, as luck would have it, is to apply this theorem. And then you just precompose over and over again until you've completely stabilized the topological behavior of the function. Now,
So what are the 6?
I'm getting there. I want to make one point before I say what they are. Again, when I say that this guy reduces this guy to an open set, I mean it's the same as saying that phi composed with C, when you apply it to the finite sequences, the closure of that is disjoint from when you apply it to the infinite sequences. And you can, right, being G delta measurable implies that you're F sigma measurable, so you can compose these two trivial facts to in fact see that you get a C with the property that the closure of the image of the infinite sequences is disjoint from the closure of the image of the finite sequences. And that means that sort of things are independent. You have to separately you can separately stabilize what happens on bare space and what happens on the finite sequences because those closures are disjoint. So what can happen? So I'm describing the behavior of this composition. On bare space it could be constant, or it could just look like the identity function on bare space. On the finite strings, it could be constant. It could be the identity function, where this guy is inheriting the topology from omega to less than or equal to omega. Or it could be an injection into a discrete set. So any pair of these gives you one of the basis elements. The other two from Slavek's dichotomy you can find in this paper. So that's one issue. In fact, when you go through the arguments to get this, you see this particular example where you're the identity here and you're a discrete set here, this comes up multiple times. And the reason why is that what these arguments are giving you is actually something better than topological embeddability. They're giving you the same thing where instead of going from the image, you're going from its closure to the closure over here. So that's a stronger notion. And there, I haven't counted, you get something like a 14-element basis. And that seems really pedantic and stupid. Why would I bother? The point is that at that level, you start to see that instead of playing this pre-composition trick, the really insightful way of seeing what's going on is no doubt to just identify a large group of dichotomy theorems, which together isolate all the possibilities. I'll mention one. I have 5 minutes. Okay. And I want to mention this one not because it's so interesting, but because the proof is so cute. So. I'm not going to keep stating all the possibilities. I know everyone wants to leave soon. So all the assumptions. So let me just say, suppose phi from x to y is Borel. Then exactly one of the following holds. Either phi is sigma precompactness preserving. I have to explain that. So sigma. So you've got your domain X. You've got a subset W of X. You've got phi going over to Y. for phi to be pre-compactness preserving on W just means that whenever you have a subset of W, which is pre-compact in X, its image is pre-compact in Y. Sigma pre-compactness preserving means that you can cover the domain with countably many such sets. 2, there's a topological embedding of a certain partial function that has no completions which are pre-compactness preserving. So there's a topological embedding of the identity on bare space where you view the domain as a subset of omega to the less than or equal to omega, but you just view the range as bare space into your function phi. Right. I hope it's clear what I mean by a topological embedding of a partial function. It's just like before. And again, I'll give you the very short proof sketch, and then I'll stop. So let G be the dihypergraph on the graph of phi consisting of all sequences xn, yn for n and n. So this is in graph of phi to the n. Such that xn, n and n converges, but yn is injective and has no convergent subsequences. It's easy to check that your sigma pre-compactness preserving if this thing has countable chromatic number, and otherwise you apply this dihypergraph dichotomy. On the domain, you do the proof of the F sigma dichotomy, and on the range, you do the proof of the K sigma dichotomy. So I'll stop there.
I'll ask one. So when you combine the identity function with the identity function on the other side, isn't that continuous?
So what you have to understand is, I made this comment beforehand. It's a good question. I made this comment beforehand that you can compose. I guess did I erase it? Yeah. What was here before? You can compose this with the G-tilde version to make sure that the thing you've dealt with has the property that this guy intersect this guy is empty. So what's going on is you have a copy of the identity function on here getting mapped over and a copy of the identity function on here getting mapped over, but their closures are disjoint, so it's not continuous.
So just to confirm, these all have very low complexity themselves, right? They're
yeah.
Just
Yeah.
the next class.
They're just the next.
No questions?
I had a question about higher levels of the Jayne-Rogers. Do we get proofs for those?
I believe I can do the next level, but I haven't verified. I haven't had yet a chance to think about this construction at the end. Remember, I said it's not enough to just apply the graph theoretic dichotomy or the F sigma thing. You also need to do this one paragraph construction, and I have yet to have a chance to think about how that goes. But the rest works.
So you have a corresponding F sigma dichotomy for that. So how do we?
Right. So there's okay. So yeah, I could say very quickly. what's the sigma 03 version, right, of the Hurewicz dichotomy, right? I mean, this sort of thing has been known forever too, but the right canonical example wasn't known. And you can see what the canonical example looks like using this open dihypergraph dichotomy. It just looks like, now I have to remember. It's this sitting within here. So it's not super nice, but this is what you see at the next stage up. And once you isolate the right graph, and the right graph is just what the F sigma dichotomy tells you it should be, then you see how this comes in.
But for functions, you already have these 6 elements, bases. So for functions, you're already done, right?
Well, this is for not being bare class 1, but what if you want to do something like not being sigma 03 measurable or not being pi 03 measurable? And I guess an addendum is that should be, level 3 should be the last stage where this particular open dihypergraph dichotomy is useful. After that level, you have to switch to continuum many dimensions, and I don't know how that goes at all.
Any questions? Comments? Oops.
Less than 10 minutes.